In 1929, American physicist Robert van der Graaf developed the Van der Graaf generator, an electrostatic generator capable of producing as much as 5 million volts of potential difference. It was originally used to accelerate subatomic particles to extremely high speeds, but nowadays, it's mostly used to demonstrate the effects of electrostatics in classrooms. Most of us are familiar with the trick of rubbing a balloon on your head and watching it seemingly defy gravity by sticking to a wall. But what has this got to do with the Van der Graaf generator? Well, they both operate on the same principle, known as the triboelectric effect. But what is the triboelectric effect? It's the process by which electrons are transferred from one material to another as they touch or rub against each other. We can use the triboelectric series to predict how this will work. This list ranks materials in order of their tendency to gain or lose electrons. If a material high up on the list, such as human hair, was rubbed against a material lower down on the list, such as a rubber balloon, the hair would lose electrons, becoming positively charged, whilst the rubber balloon would gain these electrons, becoming negatively charged. With this negative charge, the balloon is now attracted to the positively charged nuclei in the atoms of the wall, allowing it to be suspended in midair. So, how does the Van der Graaf generator utilize this effect? Well, first off, the generator consists of a rubber belt wrapped around two rollers, all housed within an insulating column. Two metal brushes are located above and below the rollers. The top brush is connected to a hollow metal dome, while the bottom one is usually connected to the ground, though in this case, it's connected to a secondary metal rod. When the rubber belt rubs across the bottom roller, electrons are torn away from the belt and stick to the surface of the roller. This is because the roller is made of a material such as Teflon, which is lower down on the triboelectric series. Over time, this buildup of electrons gives the roller a net negative charge. Meanwhile, the belt, having lost electrons, acquires a net positive charge. The negatively charged roller repels electrons in the metal brush, which travel down a wire connecting to the metal rod, making the rod negatively charged. Meanwhile, the tips of the metal brush are left with a net positive charge. Eventually, this positive charge becomes large enough to pull electrons out of the surrounding air molecules, turning them into positively charged ions. As electrons continually flow from the air to the tip of the brush and down the wire, a cascade of positive ions rush towards the negatively charged roller and stick to the rubber belt. These positive ions ride the belt up to the top of the Van der Graaf generator, where they reach the other roller, this time made from a material higher up in the triboelectric series, such as aluminium. As the rubber belt rubs over the top roller, electrons are transferred from the roller to the belt, neutralizing the positive ions and leaving the belt with no net charge as it descends back down the column. The top roller is left with a net positive charge which attracts electrons in the other metal brush, inducing a negative charge in the tips. Once again, air molecules are ionized, but this time the free electrons move towards the positively charged roller, while the positive ions left behind flow towards the metal brush where they gain electrons. As the brush loses electrons to the air, more electrons arrive in from the metal dome to replace them, leaving the metal dome with a net positive charge distributed across its outer surface. As the dome continues to lose more and more electrons, this positive charge builds and builds until it finally discharges onto a nearby object. The spark we see is the result of free electrons in the air being accelerated towards the positively charged dome and colliding with nitrogen molecules in the air, ejecting more electrons and creating positive ions. As an avalanche of electrons move towards the dome, some electrons recombine with the ions, releasing energy in the form of blue wavelength photons. This is the same phenomenon that occurs during a lightning strike. Overall, the Van der Graaf generator acts as a pump, transporting electrons from a source to a sink and creating a large potential difference in the process. Each time we see a spark, the dome gets replenished with electrons and the process starts all over again. So now you know how a Van de Graaff generator works. We hope you enjoyed the video and thank you for watching.